Hello, everybody. My name is Jinhui Yan from UIUC. I'm currently the chair for the USACM technical area of thrust for computational fluid dynamics and fluid and structure interaction. Welcome to the CFD and the FSI webinar series. Today is my great pleasure to introduce Professor Jian-Xun Wang to deliver the lecture. Professor Wang is an associate professor in the School of Mechanical and Aerospace Engineering at Cornell University. Professor Wang received his PhD in aerospace engineering from Virginia Tech in 2017 and completed postdoc training at UC Berkeley before joining University of Notre Dame as a tenure-track assistant professor in 2018. Professor Wang received many awards, including the NSF Career Award and the ONR Young Investigator Award. He currently serves as associate editor for the Journal of Computational Physics and the vice chair of the USACM Technical Thrust Area on Data-Driven Modeling. Professor Wang's research lies in the intersection of scientific machine learning, computational fluid, solid, and the thermodynamics, and uncertainty quantification. His work aimed to advance the predictive modeling, inverse analysis, and decision-making for complex physical systems. Today, Professor Wang will present an exciting topic titled Differentiable Hybrid Neural-PDE Operator for Modeling Spatial Temporal Physics. So, Professor Wang, thank you very much for agreeing to deliver the talk. We are looking forward to your presentation.
Yeah, thank you for your introduction and invitation. It's a great pleasure to present some of our work here. Actually, I'm teaching this hybrid modeling this semester and next. So I actually used some of the slides yesterday in my class. So as you know, so in my group, we are working on many different things. But in general, the central theme is to advance the computational modeling. Basically, we're interested in how to leverage, physics, data, and a numerical method, as well as the AI to build the next generation predictive models or solvers. So in today's talk, I'm going to introduce this neural differential modeling. So this is a framework we have been working on for years, and it actually provides a way to unify the physics-based PDE solver, like the CFD, and the data-driven machine learning models like neural operators, and to form the seamlessly integrated hybrid Neural-PDE solvers for predictive modeling. Particularly, I'm interested in to model or predict the complex, spatial-temporal physics. As you can see here, I'm showing you a couple of different physical phenomena from the turbulent flows, flow structure interaction to this thermal fluid coupling and all this complex, the multi-scale, multi-physics phenomena that in many engineering processes. So many of those have the complex spatial temporal behaviors, and we want to build a predictive models because it's very important for us to understand to forecast and control such complex system. So we know since most of you are from this CFD TTA, we know how do we build a model, right? So how do we build a computational model? Essentially, we are trying to start with the governing equations. If we know this is a fluid flow, it's governed by Navier-Stokes, right? And once we know this governing equations, so to make the prediction is actually to solve the equations by specifying the initial condition, boundary condition of interest. But we don't have the analytical solution for most of the scenarios, so we need to use the numerical discretizations and to convert this governing equations, PDEs, into a large system of algebra equations that the computer can understand. And this process is the numerical discretizations, and we're actually doing this numerical simulation. So this conventional, like a physics-based numerical simulation, this computational modeling paradigm has been very successful, but they are not perfect yet because first we assume that we know complete governing equations. But this might not be true for many complex physical system because there are always, I know, physics and the physics that we cannot resolve or we don't fully understand. For example, like for turbulence, we cannot resolve all the scales and up to all the scales down to the common growth scales and for any arbitrarily high Reynolds number flows. So we need a closure models. We need like the wall models. And what is the true model form? We don't know. And for many complex physics multi-scale problems, there are some physics we probably don't know the governing equations, like a complex, for example, constitutive laws for complex materials. So we don't have a complete governing equations. And even if we have the complete governing equations, and you have to specify like the input to the models. What I mean by the input is you need to specify the initial condition, boundary conditions, and parameters, the physical parameters, modeling coefficient, and then you can do the forward simulation and get a prediction, reliable prediction. But those input could be unknown or many cases uncertain. For example, we try to simulate like the blood flow in the cardiovascular system. And many of this, like the material property is patient specific, right? And we cannot do this mechanical testing for each different patient and by taking out the vessels and do the mechanical testing. So there are many parameters and boundary conditions that we don't know. So essentially we probably need to solve the inverse problem instead of doing this forward. So the conventional like computational modeling is straightforward to do this forward, but for the inverse, it's not that straightforward. And one of the barriers is actually another challenge we're facing is the computational cost because they are usually very expensive and make it infeasible or very difficult for the semantic query application, such as solving the inverse problem, propagating an uncertainty, or doing this optimization design, because you need to query the solvers for many, many times. And each simulation is very costly. You cannot afford that. And essentially, like we want to build a predictive model is to actually achieve the digital twin. So to actually build a digital twin, you need have the capability that you can almost like in real time to assimilate the observation data, the sensor data, and to do this online data simulations. And so your prediction has to be very fast. If like each prediction gonna take like hours or even days, you cannot actually to achieve like the digital twins, which is our ultimate goal. So, but the good thing is we have more and more data because of the advance in sensor technology experiment techniques, and also more like the computational power allows to do many of those high fidelity simulations. The data has been ever increased. And I foresee that the data will be more and more like in the futures. And also the hardwares. And you can see the GPU computing, the TPUs, and the hardwares has been advanced. And every year we can see the update of the GPUs from NVIDIA's, and also like there's some effort that people are developing this in-memory computing and to develop the next generation computational hardwares. And as far as the rapid development in the AI algorithms, generative models, agentic AI. So basically, we want to leverage of this like data and modern computing, GPU computing, and also like the modern AI to develop the next generation computational models, the predictive models. So how can we leverage those? So now we need to rethink about how do we, so what is the predictive models, right? So if you want to build a model that have the predictive capability or like the predictive models, in many cases, we're interested, like say, given the initial and boundary conditions and what is the steady state solutions or converged steady state solutions. You are interested in the mapping between like two spatial functions, like like from the initial field, boundary field, and to the steady state field, right? And if we want to capture the transient spatial-temporal behaviors, then usually we want to know the mapping from the like the solution at the current step and to the next step or next few steps. So once you know this mapping, you can auto-regressively simulate or emulate the spatial temporal physics. So this is also a mapping between like the spatial functions. So essentially, we want to know the mapping between functions, and mathematically they are known as operators, right? So we want to describe these operators. Once we have these operators, and we can do the predictions. So as we know, these operators can be derived from the physics. And this is actually those PD operators from the governing equation, convection, diffusions, and for this like fluid flows, and those operators to govern like the transition is actually convection, diffusion, pressure gradient, right? And to describe those PD operators, and we need to use the numerical like way, finite difference, finite volume. That is that is actually the numerical PD operators, and which is our numeric solvers, right? So like this case is actually use the Euler time stepping and to use the spatial like PD operators and to describe how this field is going to evolve. But we have already discussed the issues of this physics-based numeric PD operators in the previous slides. And alternatively, we can choose to learn those operators. And if you have a lot of data, like those data pairs, no matter current to the next steps or from the different boundary condition and correspond different like the solution field. And if you have data that we can parameterize these operators using like neural networks and use a data-driven approach to learn those operators. So this concept is known as the data-driven neural operators. It's very, very simple. And the benefit of doing this is first, if you have sufficient data, we don't need to know the complete governing equation, and if we don't even need to know this governing PD operators. And second is in many cases, this neural operator is very flexible, and you can actually define like this neural operators by directly learning the mapping from the current step into the converged steady state, or you can do this time stepping with a very large delta t on a very coarse scale, like the resolutions, and so it's really very fast. People try to build this data-driven neural operators, and one of the goals is they want to build a fast surrogate for this numeric P operators. But the thing is, they are usually very the the issue is basically this neural operators because it's data-driven models, it always have the generalizability issues. So it's really dependent on training, and if it's out of the training, let's say give a completely random generate initial condition with is out of your training distributions, and the prediction could fail, right? But that is actually the strength of the physics-based PD operator. So the natural thought is, can we leverage the strengths from the both side? And we want to kind of merge this like the to unify this numeric PD operators and with data-driven neural operators to form the hybrid structures. And the hope is it still have the flexibility and learning capability like the neural operators, but it also leverage the generalizability from the physics-based PD operators. So now we want to look at the connection between those physics-based PD operators and data-driven neural operators. And actually, there are a lot of study to study the relationship between like the numerical PD operators and also the component construct the neural operators. For example, if you consider like this PD operators, the Laplacian operators, the diffusions, and if you use a finite difference, center of like a difference, and you can write this Laplacian operators on the U is based on this center difference. You can describe this as convolutions, and so this convolution kernels is actually defined by the by this finite difference center difference numeric stencils. So basically, as you can see, there's relation that you can connect the PD operators and numeric schemes and with the convolution kernels. And there are other examples that if this is a finite volume that you can connect it to the like graph message passings, and if you think about the residual connections to build a ResNet, the building blocks for the ResNet is actually connected to the ODEs. So I don't want to expand this, but essentially, if you think about a numerical solvers, you can, if you look at this as from the neural network point of view, it's one instance of the neural networks, but all the architectures, those convolutions are predefined by the PD operators and numeric schemes you use instead of being learned from data. Of course, you can choose to learn everything from data, and that is the black box neural operators. So our goal is we want to find a sweet spot in between, and we want to form the hybrid neural operators, but the entire structure can still be trained end to end. How do we achieve that? So basically, you want to make this numerical PD operators and to implement this just like a neural network. So first, you have to make sure that they are very efficient on GPUs, and you actually build this convection diffusion like you build a convolution neural networks and leverage the GPU computing. So they should be fully vectorized. And the second is the gradient need to propagate through those numerical PD operators. So the entire like models is fully differentiable. So we need to use the differentiable programming to construct those PD operators. And within this framework, you can seamlessly couple like the trainable convolution layers, massive passings, attentions, and with the numerical PD operators like the convection, diffusion, pressure gradient, and to form the differentiable hybrid models. So here I'm showing you like one example. So if we want to build say a data-driven models or neural operators and to learn the spatiotemporal physics governed by for example, like Berger's equations. And we can choose to build convolutional like next step models. This is simple, like the simplest like next step models, for example, to describe like the transition from T to T plus one. And you can build those convolutional residual layers, but instead of construct this convolutional residual layers completely black box like a UNet, and we can choose to build these convolutions and based on the governing equations. If we try to capture the trend like the dynamics behaviors covered by for the fluid flows, we know it's covered by Navier-Stokes. So we actually use the right-hand side of the nice equation, like convection, diffusion, and pressure gradient to construct some of the convolutions and coupled with the trainable convolution to define this hybrid residual connections. And you can make it as a recurrent networks and to introduce the hidden like state and to make this as a LST. So we are not restricted as to the conventional like numeric time steppings like Euler or Runge-Kutta, but we can actually use the learnable like time steppings and to build this as a conv-STM. So overall, if you look at this entire structure, is nothing but a convolutional like LSTM, right? And if you want to train these models, we want to actually define our loss functions and based on the not teacher forcing, but based on the entire sequence. So in this way, it can reduce the error accumulations. But if you want to build a loss based on the entire sequence, that you need to let the gradient to propagate through all the component, no matter the trainable neural network component or like the numerical PDEs or PD operators are embedded into the structure. So everything has to be differentiable. So if we build this through the differentiable programming, that allow us to do this end-to-end training. So here I just want to use this very simple example to show you the benefit of introducing the null physics as a like those PD operators as a part of the neural network architectures. So here I'm comparing this PD embedded conv-STM then with the black box conv-STM. So everything is the same. The training data is the same. Everything is the same, and trainable parameters is the same. The inference cost is the same. So we treat this as both of them are data-driven models, but we want to test the generalizability. So here I'm showing you like we actually use this this model to learn the spatiotemporal like behaviors of Burger's equation, parametric Burger's equations, and we train on several different initial conditions and the different viscosities, and then we tested on completely like newly generated or random generated initial conditions and ANSI viscosities. So you actually start from the completely ANSI like random generated initial condition and let this model to roll out, right? And you want to test the forecasting and also the extrapolate like the testing on the new viscosity. As you can see, both data-driven models can work and capture the dynamics, but you can see the difference after the longer term like model rollout. So those black box models, it seems, cannot capture this sharp like shock behaviors and becomes completely unphysical after a while. And this is one of like that's the error accumulations, but with introducing the convection and the diffusions, and we actually can significantly improve the result. Remember, like the inference cost is exactly the same. So for a more chaotic system, like this 2D homogeneous isotropic turbulence, and here I actually introduced two data-driven baseline, and so in this case, the benefit is more obvious because this chaotic system, like a small disturbance or small errors, will be quickly lead to the completely different future. So without the PDEs, it will deviate from the reference at a very early stage, and with the PD introduced into this learning architectures actually match with the correlated with the reference even for this chaotic system very well. So this is a very simple design, this hybrid design, but we can see the benefit. But as I said, within this differentiable like programming framework, we can do more interesting multi-resolution design to build this hybrid structures. So this is another example that we're working on. So again, we're building this next step models. Like this is a recurrent unit. So essentially, we try to build an operator set to describe like t to t plus one, but we build this in a multi-resolution manner. So at the coarse resolutions, so we actually do the domain decompositions, and for this like your computational domain, and at a coarser level, we have the flux, and we actually use the finite volume based formulations, and we can describe those flux and based on our PD, the no PD operators. And we also introduced a global correction network to correct those flux. So basically, flux will give you the estimation of the mean for each subdomains. And within each subdomains, and we introduce a local neural operators that capture, it's actually shared by all the subdomains. And this local neural operators and try to predict or to resolve the local high frequency, high wave number features. And the average of the output of this local neural operators is actually zero. So it has zero mean, and it will add to this global predictions and at the coarser levels. And we formed this actually inspired by the finite volumes. We call this as a multi-resolution finite volume inspired network structures. And so if you know nothing about the physics, and this flux can be completely learned instead of like enforced by the PD operator. So this is kind of optional. It depends on like how much you know about the physics. So here I'm showing you that if we use this to learn the 2D Burgers behaviors at different viscosities. And here our baseline we actually use UNet because we're actually building this multi-resolution. UNet is a multi-resolution learning structures, right? So we actually make this the baseline and this Murphy net to be comparable because we actually use the same amount of trainable parameters, and the inference cost is comparable, is almost the same, and we use the same training data. And again, you can see like over the long-term predictions. Here I'm showing you this number is the number of like rollout step, but each learning step corresponds to like 1,000 numerical steps. So basically, that's a very long-term rollout. So as you can see, the UNet can, starting from the completely random generated testing initial condition and testing Reynolds numbers, and it can do the forecasting, but after a while, it becomes completely unphysical, and eventually, it's completely not unphysical compared to the reference. And the second column, the second column is actually the finite volume inspired network, this multi-resolution networks. And without equation means like we know nothing about this Burgers equations. And the third column is actually we know this Burgers equation is a coupling between the convection and diffusion. So at causal level, we actually enforce these equations. As you can see, both, even for the null equation, that just this finite volume inspired, the learning architectures can significantly improve the forecasting for like both testing Reynolds numbers. And if you look at the arrow propagations, like in these figures, so the arrow accumulations is huge for this UNet. But with the Murphy net structures, it significantly improved the result, right? Even without equation, and with equation, the arrow is much lower. So this is like a log scale. So the difference is significant, and this is like for many different testing viscosities. So the same story for this shallow water equations. I don't want and if you see that here, this is basically the UNet based forecasting. They already blows up. So now I've shown you like two examples and to show why we're interested in this hybrid models and to develop this data-driven models, because it seems more generalizable. And we are actually using the same training, same conditions, and also the inference cost is the same. Why not we introduce some like null structure from the physics we know and leverage the numerical like representation of those PDEs, because they can be formulated as a part of the neural network architectures, right? So there are many within this framework. You can do very interesting, like many different design of this hybrid structures. And if you think about this framework, if we push it to like the other end of this axis, say we know nothing about the physics, we just have tons of data, and this is more than like You can use all this modern AI architectures, attention, generative modules as many as you want. It becomes a purely black box data-driven neural operators architectures. But if we push this framework to the other end, the other extreme, that no data, we just have the physics, and in that case, that you actually need to build this neural networks completely based on the PDEs and the numerical scheme you choose, like the numerical stencil. So you can think that all the convolutions, mastery patterns are predefined instead of being learned from the data. That is our traditional numerical solver. But we actually build the solvers in a way that we built this neural networks. The two benefits. One is they are fully vectorized, and we try to leverage the GPU computing, GPU acceleration. So the solver is GPU native, right? And the second is we actually build this within the differentiable programming framework. So the solver is fully differentiable. So you can imagine that the solver have the full adjoint capability, and you don't need to derive this continuous adjoint for different applications. This in the solver, it is completely like differentiable, which means that you can get a gradient from anywhere to anywhere. So the gradient can propagate in the solver. So you can do a lot of interesting inverse design, inverse trainings, and the solver itself can be trained. If you think about this solver is like the neural network. So we are working in this areas, and we have developed a suite of the differentiable physics solvers, and for a variety of physical problems. I mean, most of them are fluid. So we developed this DiFFSI. It's a unstructured, it's a structured finite-volume solvers, and with a sharp interface, immersed boundaries, that we can handle the complex turbulence and flow structure interactions. And recently, we built this unstructured finite-volume solvers, and by formulating this as a large graph neural network set that allow us to handle the unstructured matches. And this is also fully differentiable. And we also develop a suite of the differentiable solvers for some special like a physical phenomena, like such as the manufacturing process of the fiber reinforced materials. And this JAX-BT is actually built a Farnham-Bosman transport equation, like a BTE solvers in JAX to model the multi-scale thermal heat transfers. For the nanoscale, it's actually it's not covered. The Fourier equation is not valid, so we need to solve this the BT the Bosman transport equations, and this JAX-ECM is solver for the electrochemical machinings, and we model this. So just a quick introduce of like this DiffFlowFSI as an example. So as you can see, this is a GPU native, fully vectorized, meaning there are no for loops in the solvers, and we minimize for loops, and it's based on tensor computing. It's very fast on GPUs. And the second is fully differentiable. So since it's a fully differentiable in JAX, and we use the XLA to build this solver from scratch, that allows us to actually to train neural networks or machine learning models inside the solvers. And we can do this end-to-end, like model discoveries, such as discover the closure models. And we can go beyond that because it's just modular. So we can use the part of the solver or integrate the PD operators in the solvers as a part of the neural networks, and to build the hybrid solvers or hybrid neural networks, as I show you. So here I'm showing you a gallery of the animations of the simulation that is actually from this DiffFlowFSI. Those are like the high fidelity DNS or LES simulation for the complex, the wall-bounded turbulence. Those are like inhomogeneous and isotropic turbulence. And the solver has the full capability from the DNS. And we also implement the classic smart growth scheme, SGS models, and Riemann models. You can do the LES, and including a wall model LES, we have the equilibrium wall models, and you can actually instead of resolving the wall, you can do the wall model now, yes. And we also build this vectorized differentiable sharp interface immersed boundaries. I don't want to go into those details. The idea is we actually make this goal cell findings and image points findings, and based on the sign distance functions, and make it as fully vectorized. So it's very efficient, allow us to do this flow structure interactions and prescribe, for example, like with complex geometries and with prescribed motions. As you can see, we can do this 3D vortex induced vibrations, and this is like a moving fish. And since our geometry is also differentiable, actually we can do this 3D shape optimizations, and you can see those morphing like from the one shape, 3D shape to another. So this is end-to-end from the geometries and all the way to the end of like the fluid simulations. It's fully differentiable. So that allows to do this interesting like geometry optimizations, and even like the morphing over time, and to do some interesting flow control. This is something we're interested. And this is about like the cost. As you can see, for this is like a two DNS simulation. The first one, we do this turbulent channel flows, and with 6 million mesh rate. As you can see, we compare this our Diff-FlowFSI with the OpenFOAM. So OpenFOAM is on a 32 CPU cores, and ours is on one GPU cores, and you consistently see the 30 times speed up. There's no neural net for speed up. It's just that how we implement the software on the GPUs, and it's a native GPU. So it's GPU native. So it's already very fast. And the second case is the 3D turbulence boundary layers, equilibrium turbulence boundary layers. It's a flat plate. So the DNS actually have almost like 100 million mesh rate. It's not definitely non-trivial cases. And we actually compare this the performance and with the Cascade, the academic version of Cascade, to be rigorous. So the Cascade on the 3,000 CPU cores, the time is, so it's actually comparable to our software on only like 2 GPUs. So we're pretty happy with the speed and also the accuracy. So we validate our software on a variety of the benchmark turbulence DNS simulations and FSI simulations. So here I'm just showing you a few that we compare that against with the previous DNS data and experiment data in terms of the turbulence statistics from the first order and to second order, including the spectrum. So what I want to say is they're fully reliable. So we just want to make sure that the PD operators we try to integrate into the neural network, they are reliable, right? So we want to validate the entire framework by treating this as a physics only, which is like a classic Mark solvers. As I've shown you like previously, like with this hybrid modeling, and we can of course further speed this up. And originally like by solver itself, it already have 30 times, and you can if you make this as a data-driven hybrid, and it can have a much higher speeded up, of course. And we also can within this differentiable framework that allow us to actually do some hybrid modelings, for example, like to use the like a CFD consistent way to train a closure model. For example, this is another hybrid model we built to learn the 3D turbulent boundary layers. And the goal is we want to kind of simulate the spatial temporal behaviors of the turbulence. But for turbulence, it can be viewed as a stochastic process. So most of the existing like data-driven models, they are trying to match deterministic spatial temporal trajectories. But essentially, we're not interested in like one particular realizations. We're interested in like the correct statistics, but we also want to generate the spatial temporal like realizations, right? The transient behaviors. So what we want to do is we want to actually build this hybrid models on a very coarse spatial temporal resolutions. And we try to enforce the physics on a coarse resolution, but at the same time, we also want to kind of use the trainable component and to capture the unresolved features. And traditionally, like we know this is the idea of the LES, right? So if you want to do this to achieve that, you need to use the subgrid scale subgrid scale models, SGS model to account for the unresolved scales. And since the spatial temporal resolution is so low that you also need to capture like the unresolved wall for this wall-bounded turbulence. You need the wall model. So this is naturally our baseline, which is a physics-based baseline, and this is known as the wall-modeled LES. And we actually built our hybrid models in a similar way that we use the neural network to actually account for this unresolved, like the subgrid scale effect and the unresolved wall. And essentially, we want to train these models instead of to match one spatial temporal trajectories. We just want to use the statistic to train the model. So from the machine learning point of view, this is unsupervised learning because we're not matching the UT to UT plus one. We're actually matching the overall like generated statistics because the entire framework is differentiable that allows us to do so, right? So we just use the statistics like the mean flow profiles and the RMS of the turbulence fluctuations from the train data to train the models instead of using the instantaneous velocity to train the models. But the model is still can produce the transient spatial temporal like flow state. So we are considering several testing, training testing. So the training is on a very short trajectories from the train data at the low Reynolds numbers, like RE theta 600, and we just collect two flows per time, and we only use the statistics of the train data to train a model. And the testing, we first tested start from the random generated initial conditions and let the model to roll out for like much longer tens flows per times and at the same Reynolds numbers. And the next one, we increase we make it more challenging, and we test it on not just the forecasting time, but we change Reynolds numbers, extrapolate the Reynolds number to 800, to 2400, and to 5000. So this is like RE theta. And we also want to test like with training is on a small domains and testing on a much larger, like 2 times larger, like computational domains. And we also want to test it on a different mesh resolutions. And because we know like for the wall model and LES, usually they are mesh dependent. So here is the first scenarios that we just tested on a new initial conditions and let it run for to the temporal forecasting for the 10 flows per time. As you can see, here we're actually it's very stable. You cannot see any like error accumulations, but we are not exactly trying to match the instantaneous like behaviors from DS, because this is a stochastic system. We actually generate like a different spatial temporal trajectories. It is possible. So the goal is we look at the statistics. So as you can see here, I'm showing you like the mean profiles, the the URMMS, the fluctuations at different velocity component, Reynolds stresses, the Reynolds shear stresses. So the blue one is our hybrid, and this black one is the DS, the ground truth. And here I'm also showing you the baseline model, which is the war model LES using the standard Smart-Goldskin SGS and with the equilibrium log-law based war models. As you can see, it cannot even capture the mean flows for this 600 Reynolds numbers, and also for all those fluctuations, the velocity fluctuations, they underestimate those fluctuations. But you can see this hybrid models can capture the mean and fluctuation very well compared to the DNF reference. And here I want to mention the domain size is different and the mesh resolution is different from training. And we actually run it for 20 flows per time. The war model LES does not work here is because our spatial temporal resolution is very, very low. So usually we know like you have to the LES you have to at least to capture like 80% of the eddies. So and this is the spectrum, as you can see, for the energy spectrum at different frame-wise locations. And we agree with the reference very well, but the baseline models is significantly deviate. And from this Q criterion near the wall, you can see this the turbulence has been damped out, and with this hybrid, it can capture the most of the scales very well. And this is just a 600, and we can do like extrapolation into like ANSI Reynolds numbers into 800. We actually have even high Reynolds number, but I haven't included in the slides. So even to like the RE theta to 5,000, we can still see this significantly improvement over all the turbulence statistics. And this is we actually also tested on a much larger domains. The training is on a smaller domains, but we actually tested on a much larger domains. Okay, so overall, as you can see, the spectrum and the statistics, they actually agree with the reference much better than the war model LES baselines. And we are also like working on like to train these models with even higher Reynolds numbers that from the experiment, because this whole framework is a differentiable that allow us to actually directly use the statistic from the experiment data. So we don't need really to collect the data for you know the high order statistics. So in the last few minutes, I also want to show you our recent development for another FEM solvers, but this one is completely built on for the unstructured grade. This is not trivial because we built the previous Diff-FlowFSI for the fluid part. It's on the structure, and the geometry is handled by the sharp interface immersed boundaries. But here we want to directly build this vectorized JAX-based differentiable solvers for the unstructured grade. So first challenge is very hard to do this vectorizations, right? So in short, we leverage the isomorphism between the finite volume operations and with the graph. So basically, we formulate this finite volume operations like the flux and flux aggregations, and we formulate as a graph message passing. So that allow us to very efficiently do this FEM operations on unstructured grade on GPUs. And so this solvers, and it can handle the many different type of the unstructured mesh and even like hybrid. And we also make it compatible to the OpenFOAM cases. So basically, you can consider this as you have an OpenFOAM case, like those folders, and you don't need to use like say the piece of foam, and you can directly run our DiFVM. And this is completely on GPU. So we're not relying we're not relying on the OpenFOAM. We just make this interface that you can directly use OpenFOAM, and the entire program is completely built from scratch using JAX and XLA, so it's fully differentiable that you can do this auto differentiations. And here is the isomorphism between the GN and the FEM. So basically, as you can see, we formulate this FEM on the mesh and exactly as the massive passing and for the graph. And for this flux aggregations is just the aggregation step in the graph neural networks. So previous, you have a ton of for loops and to do this linearizations for this finite volume on the unstructured mesh. And now we actually make it completely vectorized and very efficient on GPUs. So we validate this solvers and in terms of the diffusions. Here I'm showing you the comparison with this DiffVM. Sorry, this is a typo. The original name was the graph FEM, but we changed the name. So this is OpenFOAM. So the absolute values is actually less than 10 to minus 7. That we're using a single position. So that is the machine position that we can achieve. And this is a convection diffusions. And this is Lie-driven cavity. So we validate the Navier-Stokes. As you can see, they are very accurate, reliable. And this is another like a Navier-Stokes. This is the transient case for flow past any arbitrary like shapes. And we can even do like the cardiovascular, this 3D patient-specific cardiovascular simulations. And we also tested the differentiabilities, and we do the inverse models. So assuming that we don't know the inflow velocity profiles, and we actually use the flow rate at a few locations that we can infer the inflow velocity profiles and do this transient positive flows. And we also implement the long-parameter model, the Vincastles, and for this FEM solver, so it can handle like the complex, the physiological conditions, and for this cardiovascular simulations. And because it's fully differentiable, that we allow us to do this gradient-based inference of the RCR, like the resistance and capacity parameters, and using the available like observables, and to do this patient-specific parameter calibrations. Okay, so this is most of the stuff I want to share with you, and here are the other applications you might be interested. This is the postal electro machining, and we also developed the same idea, and it's the different multi-scale multi-physics problems. We actually use the electrochemical process to machine like the workpiece. So we developed this the solvers, and we validated with the experimental data from our collaborators. And more interesting that we're interested in how to like use the target shape that you want to manufacture and to optimize the tool shape. So this is what they are interested. As you can see, this is the optimization process, and based on the target shape that we can optimize the tool shape. So without that, our collaborators is actually a company that they have to, do the try and errors and try different tool shape and to see which one is actually can generate the target workpiece shape. And this is another example of this the manufacturing to model the manufacturing process of the carbon-carbon composite. And we built this multi-scale models that we used very limited data from Honeywell's, and we can build this models and to optimize their manufacturing process. And the recipe that we obtained from our predictive models has been used in Honeywell's then to actually manufacturing the carbon-carbon composite that have the higher density because you want to optimize the recipe that to generate the materials that is strong enough for the hypersonic applications. And this is another examples that we built this multi-scale heat transfer models for model the thermal management of the computer chips. So from the smallest scales, the nanoscale, which is the transistor levels, we're solving the Follow-Boltzmann transfer equations. And for the largest scales, we're solving the Fouriers. And we use the neural operators to connect those two differentiable solvers and allow us to actually do this very large scale package level thermal simulations. Okay, so I think I'm going to stop here and I'm happy to answer any questions. If you're very interested in any of those details, check out those publications I'm showing you here.
Great. Thank you, Jian-Xun, for the wonderful presentation. Now we open the floor for questions. So if you have a question, you can directly unmute yourself and ask the question yourself. Hello, can you hear me?
Yes, thank you so
Okay.
much. I had a question generally about the limitations. Thank you for the talk. It looks very impressive what you have done, but would you comment on the limitations of the method?
Sorry, so what is your question? Comment on what? I cannot
A comment on the limitations of the method. What kind of
limitation?
Yes.
So I think so the overall framework, I don't think there's like a limitation because it's actually like a framework that you connect the physics-based like numerical solver into the machine learning. So if so basically I will talk about some challenges. So first one is, as you can see this, if you want to build this, it's actually like the effort is like developing the solver from scratch. So it's not it's highly like intrusive. It's not very easy that you use off the shelf like the networks and train it with the data. And so particularly for the hybrid models, the some of the challenges because you introduce numerical like PDEs, so inherently that you will have some stability issues because like the numeric solvers, usually you need to deal with the numeric stabilities. So, but with so that will definitely make your training a little bit harder than purely data-driven trainings. So then we need some we need some like special like way to deal with the numeric stabilities and doing the training. If you think about like you introduce a completely physical like untrained neural network into the numeric solvers, and it definitely it won't sometime it will just blow up because we know like there's numerical stabilities and for any numerical solver. So this is some challenge, and you definitely need to consider. And when you build hybrid solvers, and in terms of the like generalizability, as I said, that if you move, if you remember, we have the axis. If you move like to if your data is very limited and you move to the other end, like make this hybrid models to more data driven. So you have the generalizability issues. That is a limitation. So my recommendation is based on like the data where like the goal, right? So you want to achieve. So I just want to build a surrogate models and which has I care about the speed up. I don't care about the like the generalizations outside my design space. So in that case, you can make these models to be generalizable just within this design space because that is the surrogate models I want to build, right? I don't care about too much about the extrapolations. And versus I want to develop like a more universal physics-based models and I wanted this such as for example like the constitutive laws and like the closure models to be generalizable as much as possible. In that way, you want to push this to more on like a physics-based approach, but reduce the data-driven component. Essentially, if this is more data-driven and the data is very limited, of course, you have the generalizability issues. And if you go to the other end, if it's completely physics-based, like the example I've shown you, I can completely view this as a numerical solver, right? So the best is I can achieve is the GPU solver, it's the GPU native solver, right? So but you have all the issues of the numerical solver and the physics-based models. I'm not sure if I answered your question.
Yes, yes. Thank you very much.
Okay, thank you.
Thank you. Other questions?
Okay, may I ask a question?
Yeah, sure.
Thank you for the presentation. I was wondering, I have seen previous works from you for using generative AI like conditional diffusion models. Is it something you still work on it, and what's your opinion on it? Because I haven't seen that in this presentation you talked about it.
Yeah, it's as you said, as I said, like we are working on many different directions. Yes, we are actively that is another directions that we are working on in general, like the generative AI and generative models, and we use that to model, for example, like the system itself is stochastic, like the turbulence, and more we are also very interested in like using that to model the inverse problem, because essentially like inverse model, you have the epistemic uncertainties. Even the system is deterministic because you don't know like about it, like the input, like the boundary condition parameters. So essentially, you when you solve the inverse problem, you are trying to find a posterior, right? So we are using the generative model to first to learn the solution space, which is like a prior, and we can formulate the Bayesian sampling from the based on our generated prior and to sample this posterior. So this is another direction that we are working on, and I haven't show many of those here, but we actually integrate this generative component and with our differentiable solvers. And you can imagine that we have a generative component generate the small scales for the turbulence, and we are using the differentiable solver backbone to solve or like to directly model the large scale structures, and which is more like a geometry dependent. But for general like the small scales is more universal, that we actually introduced the generative component. Yes, we are actively working on that as well. But the time is limited, so I can only cover like the one directions in this talk.
Okay, great. Thank you very much for the answer.
Mm-hmm.
Any other questions?
Hi, Professor.
Hi.
Go ahead, Adam.
So thank you for the presentation. I was just wondering, when you were comparing basically the efficiency between your solvers and say more traditional solvers, was this accounting for your training time as well? Can you talk a bit about how much time it takes for you to train, how much data you need, those aspects of it?
Yeah, of course. So in this in this talk, the most of comparison I've shown you, there's no training time. I'm actually comparing the solver to solver, right? If you remember, I'm just comparing our solver. We treat that our solver as a solver. There's no like a neural network component. So we just treat this as a GPU native vectorized solvers, on GPU, and we compare with the we are doing the same simulation, same mesh, and everything is the same on using OpenFOAM like on CPUs. So we just want to say like the efficiency if we treat this as a solver. So for the like the hybrid models, and in that case we do have the training, and we're actually comparing the cost and with other existing like numerical operators and also the solvers. And yes, we also include the training cost, but different cases you have a different training cost. And when you so what I'm showing you is the inference cost comparison. But if you really want to compare the the cost, it's depend on like how you use the surrogate. I assume when you build this surrogate, you want to just use it for one case, right? If you just use it for one case, there's no I don't think you need to build the surrogate. So essentially, the surrogate is built to cover like the DSI space, like I will show you for different initial conditions, random generated initial condition, different Reynolds numbers. And within this DSI space, and you can evaluate many different initial condition, many different viscosities. So the comparison should be like how many times you evaluate your surrogate and plus the training cost and versus that every time you just evaluate the high fidelity solvers, right? So if you use say like 10 hours for training and you just say evaluate your surrogate once and your numerical simulation say like it's also 10 hours or even like less 5 hours to finish one simulations and the speed up is maybe just twice, or even there's no speed up if you consider the training. But if you consider like you evaluate your models for like 100 times or 1,000 times, so then you are comparing like the training cost plus the inference cost of the surrogate times 100 times and versus the high fidelity simulation cost time 100 times. So that is a benefit or like the reason that we want to develop surrogate models, if that answers your question.
Thanks. Just one follow-up to that. You talk about like you showed how it's good when you vary the initial conditions or the material parameters. What happens if you, for the fluid structure interactions one, you change the location where the object is in the domain, or you change the shape? Does it work just as well in those situations?
So for the flow structure interaction, we actually change the material properties instead of the shape of the structures. If it's data driven, I don't think it will work. But if it's kind of our GPU solvers, of course, it will work as any other solver. It's just like a solver. But if there's a data-driven component, and so that definitely have its own like limitations. So it depends on if this is like I assume like the case that you mentioned, if you train these models on like one type of structures and you expect this so it depends on like the data-driven component, like where you put this data-driven component. If this data-driven component is trying to say, I'm just trying to improve to learn the discretization errors, I think it can be extrapolated to different geometries. But if you actually build the numerical solvers into the neural networks and to actually formulate the hybrid like hybrid like neural operators to directly learn the solutions, I think you cannot extrapolate to any unseen like geometries unless you let the model to see different geometries. Actually, we have that case. We use the graph neural networks, and with that model to see a different type of geometries, and it actually generates two different geometries in that case. So it depends on how you design the learning problem. So I don't have a answer for like different application scenarios.
Thank you.
Okay, Jian-Xun, thank you for the wonderful presentation. I really like it. I mean, you show the details of the methodology, and you also highlight a lot of applications. I have a question about the statistic. I mean, you use statistics to train the model, which is really interesting to me. So I have two questions regarding this. The first one is if you use the primitive physical variables to train the model, which is very straightforward because the unknowns basically are U, V, W, and P, right? Even though, I mean, the measurement can be scattered, but they are accurate and well defined. However, when you use the statistics, there are so many turbulent statistics over there, right? You have the mean fluctuation, you have also maybe the variance, you have a production dissipation. So when you use statistics to train the model, do you use all the statistics or you pick several of them to train your model?
No, we just use the very common first and second order statistic, particularly like a mean flow profile. That is
Okay.
the first order, and second order statistics include the RMS of the turbulence fluctuation, just the U prime RMS, U V prime RMS, and W prime RMS. That's only statistic we use to train the model. So when we compare, we actually compare all the different, like including the spectrum, and as you can see, the
Okay.
spectrum match with the reference very well. Yeah, we're not using all the statistics.
I see. Okay, and then my second question about this is, I mean, how you use this model in practice? Because I mean, I can imagine, right? If you use a primitive variable to train your model, I mean, it's very clear because you measure, right, at a certain point, at a certain time instance, right? You treat it as ground truth to train the model. However, if you use turbulent statistics, because in order to ensure the turbulent statistics are reliable, you first need a massive data, right, to process the statistic to ensure that they are stationary. So if you already have the
So we are
statistic, meaning,
yeah, we are actually using so when you train the surrogate models for the turbulence set, you collect some trajectories, right?
right,
Like the one flows through time or two flows through time. We'll actually
okay,
calculate the statistics from that data. We're not using the fully converged. So we actually use the statistic from like the two flows through time. That is the statistic we're using.
okay.
So it's
So
actually
even though the statistics are not stationary, it's not a problem for the training, right?
So it ideally it would be nice that you have because if you think about that, we are actually developing a better LES models, right?
Mm,
So if you have the data from the experiment from the like the other high fidelity simulations, and you want to create very fast reduced order models. So what choice you have? So typically you need to use the subgraded scale like the Smart-Goldsky and Wall model LES, where like you can build like a data-driven models completely ignore all the physics. But if you use the like the transient like those transient flows and to build such a surrogate, I believe it won't work even for the training scenarios. So if you use that to like let the model, like say you just learn a t to t plus one, or you use more like advanced, there are many such work like the transformers and to learn the trajectories. And the best they can do is they can do like the temporal forecasting. And if they even change the initial conditions, sometime like for long-term predictions, they won't have the physical predictions at what I've shown you, even not for turbulent flows, even for simple flows. So essentially for that approach, the not only the statistic would be wrong, but all the transient flow behaviors would be completely wrong. And not mentioning it cannot extrapolate to the higher Reynolds numbers. So if you build these models, like what I show you, that you actually can generate the kind of realistic turbulence, but also have the correct statistics. And even though your training is based on like the statistics from your training data. So if you're training data, you have like a 2 flows per time, you calculate the statistic from that. If you have a 10 flows per time, that would better. You have the better statistics. Remember, here we are not just rely on the statistics for our model. So the model itself, it has the physics. It is actually a solver, but the learnable component is just part of the solver. So that is why it can generalize to some on-sea conditions, and even training is not like the training data is limited or imperfect. You still have that capability. That is not magic. It's actually leverage the solver itself. right? So
Okay.
if you have a perfect solver, then you don't need any statistical data. You can still give you the reasonable prediction. So I view this as if you think of this as like a software development or like the closure modeling, it's actually a way that you try to find a better closure models and to enhance your solver. So if I put it this way, like if you just run the solvers on the core mesh and without learning any learning component, if it's still numerical stable, it will still give you something, right? It's just you don't have the closure terms, so it won't be completely wrong. But with those closure terms and like the physics-based closure, it will be better. But with this trained, it's kind of like a trained closure, but the closure is trained within the solver instead of like 10 years ago, I was working on like data-driven closure models. That is, you collect a lot of like the renal stresses and train a closure. And once this closure is trained, and you embed it into the solver. I think that, yeah, if that answered your question.
Okay, great. Yeah, thank you,
Can I
Jian-Xun.
ask, oh, can I ask a
Yeah,
question?
go ahead.
Quick
Go ahead.
question. So when you're doing turbulent flows, I don't know well about the FVMs, but like you might need some kind of like a flux limiters or filtering or some kind of like a discontinuity handling terms in the solver itself, right? Then
Yeah, you can.
most of
Yeah.
the things like yeah, most of the things about like those discontinuity part is about like a very like filtering can be linear like vectorized mapping, but if it is not like that one, like if you're doing like algebraically limiting the fluxes or other stuffs, then you will need some branchings in the solvers. Then how do you handle those?
So first, we in our case, we just use implicit LES, and most of the case that we are working on is incompressible flow. So we don't use any limit. But I think you're asking like if the software has the non-differentiable operations, how do you handle that? Is that a question?
Yes.
Yeah. So the differentiability. So basically, there are many like if else statement in the software that you can actually so many of those it actually does not actually participate in this gradient propagations, right?
Oh,
So those can be excluded from like those gradient propagations. So it's the concept is a little bit different. So your solution space, like there is a shock or discontinuities, and we are actually trying to calculate like the gradient, not like the gradient across the spatial, like not the spatial domain, but the gradient with respect to the parameters, like the parameters in the solvers. So that does not actually affect. And in the differentiable solvers and many of those non-differentiable operations, and you can clip the gradient, and that actually still make your solver to be differential. And by the way, we in our differential solver, we are not just naively use auto differentiations. So some of those are auto differentiations, and some of them coupled with the discrete adjoint. And for example, the implicit layers say different like the iterative if there is iterative schemes that for that part we actually solve a small linear system, an adjoint linear system and we connected that adjoint and with the VGPs and in the solvers and to make it differentiable. So that is how we handle those cases.
then just another quick question is like it seems you're using FP32, so right, for the solutions, but in your solvers you are not solving the linear systems or something like that, so you don't need to do like because like if the condition number of the system is very bad, then FP32 would blow up even if your solver itself is fine, right? So I'm wondering
So
like
Yeah, so the round-off errors in the hybrid learning is kind of that error source is not dominant. The dominant error source is actually from the learning. So basically that can be ignored. But if you're talking about solver only, we can do like the double position. So it just change the it's just a switch this from the single to double. The consideration is just for the most modern unless you talking about a B300 or like a previous A100 that they are very efficient for the double position, but most of the not the highest end GPUs, they are very efficient on single positions. And also because of roundoff errors is not the dominant error source, especially in a learning problem. So that is why we choose to use a single position. And to your question, we for our full solver, like a purely physics-based solver without neural network, of course, we are solving the linear system. And we actually implement the multi-grade JAX-based like linear solvers, and we plan to publish that as well. That we have the BiCG and CG, and recently we actually used the multi-grade preconditioner for this linear solvers, and especially for the unstructured irregular meshes without the multi-grade, the linear. The linear solver is you need many iterations. To be honest, yeah, we have the linear solver for sure, which
Oh
is
yeah,
also
so
differentiable
okay.
and vectorized.
Yeah, just to another, so it is just a follow-up question. Is that like so when you do FP32, you didn't have problem with it, like just the solver itself, not the learning process, but for the solver, FP32 didn't have problem with any like turbulence or anything. Like it didn't blow up the linear system or like that. Because in my experience, some of the like difficult systems like multi-phase or other problems had a like those conditioning problem, and it blows up the linear solvers in some cases. Most of the cases can be solved with FP32, but generally I believe like FP64 is mandatory for solving the systems.
Yeah, you can if you need it, you can switch to FP64, the double position for sure. And for most of the cases, even like the wall-bounded turbulence set, we actually do this test. We compare like the single position and double positions, and so the system is not as stiff that we can still solve the linear system pretty well, and with the single positions. And there's no like I know you're talking about like the for the some system that the even the small like the roundup error is going to lead to the because the condition number of the system is pretty bad, right? So we don't have that problem, but I mean like if you need the double position, you can just switch to FP64 as you want.
Then how is the performance different? Is it like just a 2 times slower, or like I
That's not
understand
too
that
hard.
depending on the GPUs it changes, but
Depend on
like
you.
if
Yeah,
the
I can
yeah,
actually
so
give you I can give you the ideas. For example, we're using the A6000. So the
mhm.
performance difference is less, is just 1.3 times. Basically, there is some overhead for that double position, but not 2 times.
Okay. Okay, thank you. Thank you.
Okay, great. It has already been almost 1 hour and a half. So in light of the time, probably we should end the webinar. So let's thank Professor Wang again for the wonderful presentation. Jian-Xun, thank you very much.